Mevrouw Director Magnificus, Meneer de Decan, my dear colleagues, family and friends, good afternoon. I'm honored to see you all here and would like to welcome you to this inauguration talk. To start my presentation this afternoon, I would like to first quickly read for you the short abstract of my talk, which is distributed to the media. The talk is about collaborative adaptive systems, CAS for short. And while I'm reading this short abstract, you can watch parts of the process of manufacturing the Airbus A380 on the screen next to me here, where different parts of this airplane are manufactured in a distributed manner, and then they all arrive to the final assembly site by different means of transportation to be assembled. This is a simple example case of collaborative adaptive systems composed of a number of organizations, individuals, and intelligent devices that collaborate to achieve the common goal of their constituting systems. Today's society has a socio-technical structure operated by systems that primarily consist of collectives of heterogeneous technical components and autonomous actors. To compete and survive, these collectives engage their components in flexible, evolving networks, wherein they function and collaborate toward achieving their common goals. Units such as individuals, organizations, and intelligent devices constitute the actors in such collaborative adaptive system, which may involve different temporal and spatial scales. Typically, the boundaries of a CAS are fluid, although in specific cases, a CAS may involve only tightly tangled nodes and may choose to operate as a closed border network. In my research group, we develop high-level models to study the collaborative interactions within a distributed CAS. We address design, development, and operating principles of the CAS, with challenges including collaboration process definition based on competencies, reference modeling and analysis, engineering the behavior of both the single agent and collective of agents based on their exchange commitments and agreements, data and service sharing and composition infrastructures, intelligent decision support, and consensus on common perceptions of valuation and reward and sanction. What you're watching here is parts of the operation stage of a complex adaptive system, which is composed of many smaller subsystems involved in manufacturing, logistics, and assembly of the Airbus planes. I have selected the Airbus manufacturing as a simple example to start with because, in fact, in the European project, Ecolit, we had the opportunity to work directly with a large network of organizations called Isoin Helisei. Isoin Helisei is involved in exactly this manufacturing process through producing some of the subsystems in this collaborative adaptive system. Isoin includes more than 90 small and medium-sized enterprises that together have more than 4,500 employees. In fact, please notice that all the applications that I mentioned this afternoon in this presentation have some relation to some of the projects in which we have been involved at FCN. So, collaborative adaptive systems are collectives that form continuously evolving systems with common goals and diverse decision-making actors. The actors are organizations, individuals, or intelligent devices. CAS has a virtual collective presence, and actors in the CAS have joint responsibilities, which means they must flexibly adapt, collaborate, and function to achieve the common goal, which is the reason for the existence of the collective. And IT infrastructure constitutes the base for the communication. Research on CAS is transdisciplinary, and there are many different disciplines involved. The computer science is the main discipline, but besides that, organizational science, management, social science, and law are also some of the disciplines that have to work together in order to be able to support this collaborative adaptive systems. So what are the computer science challenges on CAS? It involves both structures and algorithms. There are three main areas that are involved in the research in computer science in this area on CAS. One area is theoretical area, which mostly involves multi-agent and logic. The second one is methodological area that involves multi-agent reasoning, machine learning, and mining. And the third area is experimental area, which involves software engineering and databases. In the theoretical area, there are three sub-areas that are mostly researched on. Formal model of behavior, both for individual agents and for the collective of agents based on the tasks that are allocated to them and the fulfillment of the exchange commitments and agreements between them. The second sub-area is formal model of collaborative interactions, which is considered both inter- and intra-distributed CAS interactions. The third sub-area is formal model of valuation, which is to achieve a common perception of rewards and sanctions. The second area is the methodological area. This one has several sub-areas that develop methodologies that are needed for CAS to function efficiently. First sub-area is interoperation, procedures, and processes. So this is about the procedures for data and service exchange and composition. Second sub-area is coordination, supervision, and evolution, monitoring agents and collectives and their dynamic decision support. Third sub-area is risk analysis and prediction of undesired situations. Fourth one, competency-based partner search and collaboration process definition. The third area focuses on experimental experimental aspects of the CAS, and it includes infrastructure for interoperation, applying service orientation, developing federated databases, networking, etc. When it comes to collaboration among agents, among autonomous intelligent agents, the issue of betrayal also comes up. There are certain social dilemmas related to uncertain transactions when we consider the collaboration. And a few examples of games are analyzed in game theory. For example, Prisoner's Dilemma, Tit for Tat, Ultimatum Game, Tragedy of the Commons, which all prove the benefits of betrayal in case of uncertainty and show why two rational individuals might not in fact cooperate, even though it might be to their best interest to do so. However, no matter what the above games forecast, in reality, both humans and organizations display a systematic bias towards cooperating. In fact, this becomes more clear when we consider the games that are really played with people at different universities, and the results always show that you know, the work is more cooperative, or the decisions are more cooperative than the theory based on rational selfish actions predicts. And similarly, we see in business the same trend that businesses show cooperation more than betrayal. Open source community of Wikipedia is one example. Free training of suppliers by Toyota that also go and benefit the other manufacturers of cars is another one. Opening software systems to software communities by Google, and many other industry examples can be given. These movements are in fact not out of altruism, but rather they're based on the realization of that the collaboration is beneficial if they want to sustain the success. Besides the CASs that are actually involved in the industry, and I mentioned them, during the last 4 decades, there are a few other phenomena that enable CASs. On one hand, there is evolution in society and market. For example, advances in ICT, emergence of internet, pervasive computing, increase in the complexity, number and size of the social, scientific, and business problems, globalization, increase in entrepreneurship, etc. On the other hand, there are research advances in collaborative networking. For example, understanding and modeling the collaboration in networks better, development of new collaboration concepts and theories, implementation of supporting mechanisms and systems, addressing large number of new and diverse applications, emergence of new digital ecosystem and collaborative adaptive systems, etc. I'm going to point to a few examples, just shortly point to them, so that you get an idea of what are the environments that are heavily using CASs. Civil construction, building bridges and highways and airports is one of the oldest areas in industry that needed to use collaborative adaptive systems. We have a large number of expertise that are needed. All of them are niche areas, from designing to digging to basing the columns, construction, control setting, maintenance, testing, everything. And these are not the expertise fit into one organization. Rather, there are many organizations that are each experts in this area, and they have to be properly put together and networked, and then the collaborative planning and scheduling should happen for them. Just to show you in this one example, what are the elements that we have to be carefully considering when we want to generate a formal model. I put a few of those elements here. For example, we have to consider the collaboration in this case is opportunity-based. It's not a continuous production. It's actually not permanent. The CAS is not permanent while it is a long-term environment and long-term collaboration. Networks of organizations and people and individual devices and the intelligent devices, and they are autonomous, heterogeneous, geographically dispersed, and they all have their own norms and idiosyncrasies. The interrelationships are pre-established. The contracts are mostly bilateral. There are both complementary and duplicate competencies. Duplicate competencies are needed for generating higher capacity that is needed. The interrelationships are pre-established. They share resource, skills, and profit and losses. There are some joint responsibilities and liabilities that have to be supported. The dynamism of the network is due to both internal and external events that happen all the time during the long term that the civil construction is ongoing. There is heavy negotiation, etc. A few other examples just to shortly mention: emerging renewable energy application, where there are many organizations involved in energy production, storage, distribution, consumption in an open market, is a good example of the need for collaborative adaptive systems. Emerging sensor network, that's another one. The example that I have put here is the community-oriented management and monitoring of natural resources, where we have large number of sensors that measure different elements, different parameters of the environment: temperature, pressure, chemical concentration, etc. Every one of these sensors, in fact, can do some little computation. So they collect the data, they do some processing, and then they send the processed and raw data to a central node that integrates different data and then makes the decision based on what should be happening next. The last example that I want to mention here is emerging intelligent transportation system. Here we have organizations of large number of them and a large variety. The municipality authorities, for traffic management, the highway concessionaires, the parking, the gas station, even the restaurants on the road, insurance company, etc., should all be able to work together in order to develop integrated transportation service to support the drivers on the road. Now, from all these CAS experiences in practice, there are a number of intuitive realizations about the collaborative networks that are achieved. For example, there are diverse actors in this environment: autonomous, heterogeneous, geographically dispersed decision makers. There are two main kinds of networks: goal-oriented networks, for example, the opportunity-based virtual organization that we have all heard of, as well as the long-term associations, and that is what is called breeding environments for virtual organizations. The main life cycle phases of CASs are already identified: creation, operation, dissolution. The support functionalities that are needed for it, for opportunity identification and characterization, selection of partners, negotiation, etc. So what do we do? Considering that CASs are so complex, and with this background, I'm now going to tell you how we approach CASs and what we do about collaborative adaptive systems at FCN. As a base definition, any network group of interacting agents, individuals, organizations, and intelligent devices with distinct properties and behavior, and using the internet as a passive communication medium is considered a CAS. There is a sharing of common goals, and there is exposing dynamic behavior that we can see from the agents. CASs are characterized by distributed decision-making and control. and they exhibit what we call dynamic evolutionary aggregate behavior. Now, this is due to the fact that actually there is emergence of unanticipated behavior all the time at the CAS. And this unanticipated behavior is caused by perhaps contracts being too coarse-grained, not defining the detailed tasks that every agent should do. There are some endogenous events. A partner or organization falls off or leaves the CAS, or there can be exogenous interactions like what happens in the environment, for example, during the construction of a bridge. Fulfilling joint responsibilities, agents, self-organizations, etc., that I'm going to describe in the next few slides. So there is dynamic change in agents' interaction and task allocations. So there is let's say, interplay between collaboration and competition. In CAS, the agents are organized in a system that aims to maximize the synergy in this network. Agents are autonomous and heterogeneous input-output systems. They have conflicting goals. They are competing, collaborating, or betraying. They have norms and idiosyncrasies, and the resources and products that they produce are of the kind matter, energy, knowledge, information, etc. The coupling or organization are alliances that are formed for co-working. So the tasks are divided and allocated to agents, but then the organization cannot be only imposed from above. Rather, it should be also voluntary and self-intended collaboration or self-organization. I explain later. The synergy needs to be maximized, and for that, there should be measurement of system performance. So we have to monitor the agents and collective behavior, and the activities should be supervised and coordinated, and there should be a reward and sanction mechanism. This is one example of emergence of voluntary or self-intended collaboration and self-organization. This is where, for example, an agent that was supposed to generate the mold eye announces that he cannot do the job. Immediately, the task leader goes to the group that he is leading and suggests who can take over, and the different agents may suggest that they can take it over, but then the task leader tries to match the capability of one of the agents and then matches it with the description of the mold and decide that Agent J can be selected to replace Agent P, and then Agent J should give a promise and make the commitment to perform that task. So this task was not there before, it just came up, and this happens quite often actually in CASs. Now, what is the adaptation and self-organization? Agents can adapt their behavior and planned actions, and they can also self-organize themselves. This is what we say. So what's the meaning of it? There are two forms of organizations. There is imposed organizations, which is top-down, where the structure pre-exists, the roles and relationships among the agents are all known. And there is self-organization, which is bottom-up. That's where the roles and relationships are not known. So it requires that the agents that are self-organizing can agree on a common goal and also have the ability to self-structure and define their roles and relationships with the others. Now, CASs are neither. CASs are hybrids with dynamically evolving behavior, which is a merge of the top-down and bottom-up organization, interaction, and decision-making. In fact, the supervision and coordination in CASs are mostly imposed, while the structure definition and roles and relationships among the agents are mostly self-organized. Now, about the unanticipated behavior emergence in CAS, emergence can be synergetic or frictional. So there is variation and selection involved, and there is mutual adaptation that occurs among agents through coupling. And this coupling can be either to maximize the generated value, or it can be to achieve an intended synergy or friction. Now, since the agents are the local decision makers and they're independent and autonomous, they can make decisions at the local level, which is beneficial for them. No matter what kind of decision they make at the local level, if it is optimal globally, then that is considered synergetic. And if a decision whatever it is, optimal or not at the local level, is not optimal globally, then it's called the friction. Some examples of emergent properties in CASs, two examples I'm giving here. For example, appearance of a new goal, not originally explicit in the constituent subsystems. It can be synergetic or frictional, it doesn't matter. The new goal is an emergence of an unpredicted behavior. Another one is when one small action taken by an agent can have unanticipated outcome at the micro level. That is another unanticipated synergetic or frictional behavior. There is an interplay between adaptation and self-organization in collaboration. Self-organization can emerge out of random interaction among autonomous agents if the collaboration is rewarding. So usually agents start with certain interactions. Every component interacts with another, and there is competition and conflict. There are some random variation in the state of the components with respect to each other. But then it comes to the point of selection. If selection is not random, which means there are positive experiences and arrangements get reinforced and pursued from the involved components, and negative experiences and arrangements get weakened so that they're discontinued, then eventually self-organization appears, and it causes the system to stabilize in collaboration. Mutual adaptation and coordination or self-coupling between the agents happen, and activities and states of components become mutually coordinated, and the propagation of the fit happens. So self-organization is quite fascinating, and it manifests in everywhere, in all the time, in many aspects of life. We have all seen the harmonious, flux of flying of the flocks of birds and the fish in the fish tank, etc. However, the question is, if self-organization is going to take care of stabilizing the castles in collaboration, then why not only follow that? Well, there are many reasons for it. For example, besides the typical lack of performance, wasting of assets, reduced quality of results that happens until the stage where a CAS can, in principle, reach a self-organization. Besides that, there are two main counterexamples that I would like to give here. One is on unintended damage, and the other is intended damage. Unintended damage is, for example, the frictional antispiral is one of those. Antispiral ant mill is an observed phenomena in a group of army ants. Let me see if I can show it to you here. So what you see here is the army ants that are separated from the main foraging party. They lose the pheromone track and begin to follow one another. Forming, I cannot stop that, forming, a circle that is continuous, and they continuously rotate, in this circle until they eventually die of exhaustion. So besides the unintended damage, there are also intended damages. That's another counterexample, and that is frictional self-organization, for example. This is where the assets of the network can be hijacked hijacked in a way which is not furthering the common goal, which is not optimal globally for the network. And while you may consider or think that the first example, like the frictional antispiral, it may seem an extreme example, and it will not happen that often, although it does sometimes. For example, we have the global warming, and this is a good example of frictional antispiral situation. But nevertheless, the second case, which is the intended damage, happens very frequently from time to time in cases, and it's not rare at all. So how can we help it?
Can we improve the quality and achievements of the CAS in this specific kind of CAS socio-technical ecosystems? Can we enable them in a way that they can avoid these kind of problems and become efficient and produce better? The answer is yes, and this is what we're doing in my group at the FCN group since 1994. So, first step is to focus on avoiding conflicts. So this occurs frequently, conflicts between the agents. And it happens due to the diversity of the agents and the potential competing that they do with each other. This happens in dynamic and complex environments quite frequently. So besides that, how to ensure that organizations effectively can collaborate, support the common initiative, respect joint policies of the CAS, to go towards and further the CAS towards its common goals, contribute proactively to the joint responsibilities, etc. So this is what we do. I showed you a slide similar to this earlier on, and told you that there are challenges in computer science for CASs. What we do is we develop both the needed structures as well as the needed algorithms. And the research in the group actually divides into three main areas: collaboration modeling, which is the theoretical work; collaboration means, which is the experimental work; and collaboration coordination, which is the methodological work. Under collaboration modeling, we focus on understanding a structural characterization and formal modeling of CASs. We understand and do the descriptive modeling of CASs. So we apply multi-agent environment and model the properties and features. We develop taxonomy and reference frameworks for CAS. I'll show you ARCON, which is the reference model we have developed for CAS, applying set theory. Formal models of behavior, interaction, and valuation. We apply first-order logic here. The collaboration means, which is the experimental part of the work, focuses mostly on developing data and service interoperation infrastructure for CAS, federated data interoperation and federated service interoperation infrastructures. The collaboration coordination, which is the methodological part of the work, focuses on designing methodologies and algorithms for CAS for risk analysis and optimization, distributed supervision and coordination, prediction, and intelligent decision support. Now, in the little time that I have left, I would like to give you some examples of what we're doing in relation to all of these. So I put all of these actually in the chart as you see down here. And I have divided it in the way that I mentioned it. And then here I put the examples of funded R&D projects as well as the other research that we're doing. And I put a cross next to what we do in which project or which research. So I'm going to now pick some of these crosses and explain them for you. First one. The theoretical work that we do on understanding and descriptive modeling of the CAS, as well as taxonomy and reference framework, this work is done in EcoLead project. Besides the identification of, carefully identifying the stages of the life cycle of the CAS, which is actually what you see there. And identifying all the stages. I mean, especially, it's good to pay attention that the operation stage involves a number of evolution stages by itself. After identifying this, these actually were put on one of the axes of the reference model for CAS, and then next to that on the other axis we have the endogenous elements and the exogenous elements. Endogenous elements constitute aggregational, structural, behavioral, and functional aspects, and exogenous interaction, market support, societal, and constituency. Besides this, we have done a taxonomy of CASs, identifying and classifying all different forms of CAS that can occur. And next to that, we have done an ontology, a reference ontology for the reference model of CAS that we have designed. And here we have, in fact, developed 10 sub-ontologies for it. And one of those 10 sub-ontologies is focused on the ontology for the competency of the actors in the CAS. Next research that I would like to mention is actually in the experimental area and related to federated information interoperation infrastructure. This is actually done mostly in two R&D projects, EMBI and LifeWatch. Here, what the situation is that we are dealing with a number of nodes of different kinds: observation site, processing site, research site, repository site, collection site. Every one of them has its own legacy databases, and they want to share and exchange information. In order for them to work together, first we have to come up with a single schema, federated schema for the site. And for that, we actually developed an automated way of matching the elements between the two schemas, the donor and recipient schemas, two schemas at a time. We are going to integrate them, and at the end, we reach a federated schema that is common to all of them. And for this schema, we have actually done the syntactic matching, semantic matching, and structural matching. Next to doing this, through the matches, we actually extracted a set of derivation rules. And these derivation rules say how these elements are connected to each other. The use of these derivation rules is actually in federated query processing, which means after we develop a federated integrated schema, then the queries can come and can go and find their answers through accessing and crawling into the legacy databases and getting all that information back. So this is the work that we have done in EMBI and Lafarge. Next thing I would like to mention is actually a methodological research that we have done. So here the emphasis was on prediction and intelligent decision support. The work is done is actually on the trust assessment methodology, and the work is done in the ECOLIT project. One issue to notice is the fact that the trust is not an absolute value. I always give this example that you trust your dentist to fix your teeth, but you should not trust the dentist to fix your dentist to fix your car. So trust is not an absolute value, and it very much depends on the perspective for which the trust is being measured. So what we do is that we actually first considered the CAS and identified a set of perspectives, five perspectives: structural, social, economical, technological, and managerial, under which the trust can be measured. And then from there, we actually identify a set of requirements and then a set of trust criteria that are measurable. And these can actually identify the generic, let's say, valuation of the organizations in terms of trustworthiness. But to make it real, in fact, we developed a methodology that relates these generic set of trust criteria to the specific factors that describe the application environment. And through a causal analysis of interrelationship between these elements, we were actually able to extract a computational formula that let us assess and measure or compute the trustworthiness of organizations in the CAS. Now, this was actually developed, the replicable, customizable methodology that we have developed was developed in ECOLIT for manufacturing area, while actually ever since it's being applied to several other areas, such as seafood processing last. Next thing that I would like to mention is actually partially a theoretical part of our work and partially a methodological part of our work, and this relates to the supervision and coordination and formal modeling and reasoning about the behavior of organizations. So this work is actually done in collaboration with University of Utrecht, and what we do is that we first define three kinds of norms: contract-related norms about joint promises, consortium-related norms about prescriptive and prohibitive norms in the environment, and the activity-related norms which formalizes the individual promises. After formalizing these definitions, we actually go and work on the state of the promises, like conditional, withdrawn, released, dissolved, etc. And then with using first-order logic, we formalize these definitions so that we can then monitor and supervise CASs, so that we can reason about the individual and collective behavior in CAS, do the risk analysis and predict the health of the CAS and activities that are occurring inside the CAS, and coordinating CAS activities and its evolution. Next, I would like to mention something about a work that we're doing, partially experimental and partially methodological. This is about uncertain data integration from heterogeneous sources and identity resolution. I mentioned in an earlier talk what we did with integration or federation of databases that are certain. This work focuses on uncertain databases and how we can integrate them. And here, actually, the automated schema that we automated, instead of federated schema that we had there, here we have a set of schemas, each of them with a probability of correctness. And we have developed a mechanism, a methodology for automated uncertain data management and integration. And further to that, we have done also work on automated uncertain entity resolution. And here, it's about the fact that given an entity, we want to find all the tuples and all the related information belonging to it with the highest probability from all the sources on certain databases that we can gather it from. And we develop efficient approaches, context-free and context-sensitive similarity functions that produce better results than other algorithms. Last thing that I would like to mention is actually partially the experimental work that we are doing. And this work is about the business service discovery and composition in CASES. Part of the work is done in GLONET project, and the other part is in collaboration with CWI. We address generation and integration of composed services in CAS through reusing the existing shared services. So imagine that we have shared services inside an environment, and we want to be able to develop integrated services by reusing them and knowing what they are. But the first thing that we need here is actually to develop a new meta model, and this new meta model should unambiguously specify the syntax, semantics, and behavior of those shared services. Besides that, we also develop an implementation of a framework that supports the service manipulation, that applies the meta model, and then supports the user with service discovery, adaptation, composition, and execution monitoring. What next? Focusing on distributed supervision of systems. And here the complexity is actually quite interesting. We are focusing on systems such as security systems of systems and intelligent transportation systems of systems. And what we want to do is, in fact, formalize and enforce collaboration in order to enhance these environments. So we monitor the agents for both normal and idiosyncratic behavior. We assign values to agents' actions, performance, utility, payoff, fitness, etc. We measure the performance and behavior of the agents, and for that, for example, we look into how they perform the allocated task, what is the level of collaboration, selfish or altruistic behavior of different agents' reputation, in collective actions that they do with the others, etc. This is a topic map of all the, let's say, areas that we have worked on. And in fact, what you saw in the topic map was only made out of the titles of the papers that I showed you. Now let's see if this has sound. So, would you now recognize the cast when you see it? I sure hope so. I would now like to first acknowledge and express my sincere appreciation for the support that I receive from the Board of the University of Amsterdam, the Board of the Faculty, and the Dean of the Faculty of Science. Furthermore, I would like to thank the co-authors of all the publications that I have had in the last so many years, as well as the external funding that I have received, and it's mostly from the European Commission, but also some national ones. Furthermore, many people have helped me through the years to arrive at this point in my life and stand here in this position in front of you. They certainly deserve to be thanked for helping me out in one way or another. First, I would like to express my sincere gratitude to Peter Sloat, Peter Adrians, and Jan Berstra that at different times acted as directors of our institute and supported my promotion to this position in their own ways. They have also all three of them acted as a source of encouragement and have helped me with finding solutions to challenges on the way. I would also like to thank all my old and new colleague professors at the Informatics Institute, a few of whom I know since I joined University of Amsterdam as a younger scientist. I would also like to thank the members of the Administration Office, Financial Office, System Support Group, and the Secretariat of the EV that carry the weight of this institute. And during the years, each of them at one time or another have helped me to get by and facilitated my work at UFA. My special thanks goes to Eric Hittepia, who has helped me in recent years and is in fact responsible for arranging this entire inaugural event. Thank you very much, Eric. I would like to thank my family members, my sister, and all my friends who could attend this event. I'm certainly thankful to my husband, Farad, who cut his sabbatical at Stanford short so that he can be present at this event. I'm certainly blessed and honored to have my family and friends in my life. And now one last appreciation, which I like to do in Dutch, one sentence in Dutch, to honor my two wonderful daughters who have in fact gone through the entire Dutch system of education with not much help in Dutch from my husband and I, who unfortunately do not know Dutch well enough to help. What makes me very proud is that today they are both PhD students in Dutch universities. My older daughter Tara studies neuroscience at the SILS Institute at the University of Amsterdam, and my younger daughter Manda studies stem cells at the Hubrecht Center in the University of Utrecht. So in their honor, I would like to say in Dutch, ik sprak over mijn werk, maar het hoogtepunt dat ik het meest trots op, mijn twee dochters. Okay. Without the people in my group, I could not have done what I've done, so I'm very thankful to all of them and their contributions. And now, without further ado, I would like to ask you all to join me for the reception. Please do not form the traditional line at the beginning to first talk with me. Rather, please take something to drink and eat, and we will catch up later. En nu, ik heb gezegd. We have to wait for the lady, or should we go?